Let's complete the proof of the master method. Let me remind you about the story so far. The first thing we did is we analyzed the work done by a recursive algorithm using a recursion tree. So we zoomed in at a given level j, we identified the total amount of work done at level j, and then we summed up over all of the levels, resulting in this rather intimidating expression star. C n to the d times a sum over the levels j from 0 to log base b of n of quantity a over b to the d raised to the j. Having derived this expression star, we then spent some time interpreting it, attaching to it some semantics, and we realized that the role of this ratio a over b to the d is to distinguish between three fundamentally different types of recursion trees. Those in which a equals b to the d, and therefore the amount of work is the same at every level. Those in which a is less than b to the d, and therefore the amount of work is going down with the level. And those in which a is bigger than b to the d, in which case the amount of work is growing with the level. This gave us intuition about the three cases of the master method, and even gave us predictions for the kind of running times that we might see. So what remains to do is really turn this hopeful intuition into a rigorous proof. So we need to verify that in fact the simplest possible scenarios outlined in the previous video actually occur. In addition, we need to demystify the third case and understand what the expression has to do with the number of leaves of the recursion tree. Let's begin with the simplest case, which is case 1. Recall in case 1, we're assuming that a equals b to the d. This is the case where we have a perfect equilibrium between the forces of good and evil, where the rate of subproblem proliferation exactly cancels out with the rate at which we do less work per subproblem. And now examining the expression star, we can see how easy our lives get when a equals b to the d. In that case, this ratio is equal to 1. So naturally, this ratio raised to the j is also equal to 1 for all j. And then, of course, this sum evaluates to something very simple, namely 1 summed with itself log base b of n plus 1 times. So the sum simply equals log base b of n plus 1. And that's going to get multiplied by this c n to the d term, which is independent of the sum. So summarizing, when a equals b to the d, we find that star equals c n to the d times log base b of n plus 1. Writing this in big O notation, we would write big O of n to the d log n. And again, I'm going to suppress the base of the logarithm. Since all logarithms differ only by a constant factor, we don't have to specify the base. That's just suppressed by the constant hidden in the big O notation. So that's it for case 1. Like I said, this is the easy case. So what do we do when a is not equal to b to the d? And remember, a can be either less than or bigger than b to the d. To answer that question, let's take a short detour into geometric series. For this single slide detour, we're going to think about a single constant number, r. Now, what you want to think about is r representing that ratio a over b to the d from the previous slide. But for this slide only, let's just call it r. This is a constant, it's bigger than 0, and it's not equal to 1. Now, suppose we sum up powers of r, stopping, let's say, at the kth power of r. I claim that this sum has a nice closed form formula. Specifically, it is exactly r to the k plus 1 minus 1 divided by r minus 1. Now, whenever you see a general formula like this, it's useful to keep in mind a couple of canonical values of the parameters that you can plug in to develop intuition. And for this expression, you might want to think canonically about the cases r equal 2 and r equals 1/2. So when r equals 2, we're summing up powers of 2, 1 plus 2 plus 4 plus 8 plus 16, and so on. When r is 1/2, we're summing up 1 plus 1/2 plus 1/4 plus 1/8, and so on. Now, I'm not going to prove this for you. I'd like you to prove this yourself if you don't already know this fact. So the way to prove this is simply by induction, and I will leave this as an exercise. What I want to focus on instead is what this fact can do for us. The way we'll use this fact is to formalize the idea that in recursion trees where the amount of work is increasing in the levels, the leaves dominate the overall running time, and where recursion trees where the amount of work is decreasing in the level, the root dominates the running time, in the sense that we can ignore all of the other levels of the recursion tree. So in the notation in this slide, we have two upshots. First of all, for the case when r is less than 1, and in this case, this expression on the right-hand side, r to the k plus 1 minus 1 over r minus 1, can be upper bounded by 1 over 1 minus r. So again, remember, you might want to have a canonical value of r in mind here, namely 1/2. So what we're claiming here is that the right-hand side is no more than 2 for for the case of r equal 1/2. And that's easy to see if you think about 1 plus 1/2 plus 1/4 plus 1/8 and so on. That sum is converging to 2 as k grows large. So in general, for r less than 1 and constant, the sum is bounded by 1 minus 1 over r. Now, we're not actually going to care about this formula, 1 minus 1 over r. The point for us is just that this is a constant. And by constant, I mean independent of k, independent of how many terms we sum up. Obviously, it depends on r, the ratio, but it does not depend on how many things we sum up on k. So the way to think about this is when we sum up a bunch of terms where r is less than 1, then the very first term dominates. The first term is equal to 1, and no matter how many terms we sum up, we never grow bigger than some constant. A similar situation holds for the case where r is a constant bigger than 1. When r is bigger than 1, a tiny bit of algebra shows that we can upper bound the right-hand side by r to the k times something which is constant, independent of k. So again, let's interpret the second upshot in terms of a canonical value of r, namely r equals 2. Then our sum is 1 plus 2 plus 4 plus 8 plus 16, and so on. And what this is saying is that no matter how many terms we sum up, the overall sum is never going to be more than twice the largest and final term. So if we sum up to, say, 128, the sum, you'll notice, will be 255, which is at most twice that largest term, 128. And that same is true for any k. The entire sum is no more than twice that of the largest term. In this sense, the largest term of the series dominates the whole thing. So to summarize this slide in just one sentence, when we sum up powers of a constant r, when r is bigger than 1, the largest power of that constant dominates the sum. When r is smaller than 1, then the sum is just a constant. Let's now apply this to prove case 2 of the master method. In case 2 of the master method, we assume that a is less than b to the d. That is, the rate at which subproblems are proliferating is drowned out by the rate at which we do less work per subproblem. So this is the case where the amount of work is decreasing with each level of the recursion tree, and our intuition said that, well, in the simplest possible scenario, we might hope that all of the work up to a constant factor is being done at the root. So let's make that intuition precise by using the basic sums fact on the previous slide. So since a is less than b to the d, this ratio is less than 1. So let's call this ratio equal to r. So r, you'll notice, does depend on the three parameters a, b, and d, but r is a constant. It does not depend on n. So what is this sum? This sum is we're just summing up powers of this constant r, where r is less than 1. What did we just learn? We just learned that any such sum is bounded above by a constant, independent of the number of terms that you sum up. So therefore, what does this expression star evaluates to? It evaluates to c, which is a constant, times n to the d times another constant. So suppressing the product of these two constants in big O notation, we can say that the expression star is upper bounded by big O of n to the d. And this makes precise our intuition that indeed the overall running time of the algorithm in this type of recursion tree with decreasing work per level is dominated by the root. The overall amount of work is only a constant factor larger than the work done merely at level 0 of the tree. Let's move on to the final and most challenging part of the proof, the final case. In case 3, we assume that a is bigger than b to the d. So in conceptual terms, we're assuming the rate at which subproblems proliferate is exceeding the rate at which we do less work per subproblem. So these are recursion trees where the amount of work is increasing with each level, with the most work being done at the leaves. And once again, using the basic sums fact, we can make precise the hope that, in fact, we only have to worry about the leaves. We can throw away the rest of the work, losing only a constant factor. So to see that, we will again denote this ratio between a and b to the d as r. And in this case, r is bigger than 1. So this sum is a sum of a bunch of powers of r where r is bigger than 1. What did we just learn about that 2 slides ago in the basic sums fact? We learned that such sums are dominated by the largest and last term of the sum. Okay? So they're bounded by a constant factor times the largest term. Therefore, we can simplify the expression star to the following. I'm going to write it in terms of big O notation, and like on the last slide, I'll use it to suppress 2 different constants. On the one hand, I'm going to be suppressing the constant c, which we inherited way back when from the original recurrence. And on the other hand, I'm going to use it to also suppress this constant that comes from the basic sums fact. So ignoring those 2 constants, what do we have left? We have n to the d times the largest term of the sum. So what is the largest term of the sum? Well, it's the last one, so we plug in the biggest value of j that we're ever going to see. So what's the biggest value of j we're ever going to see? Well, it's just this, log base b of n. So we get the ratio a over b to the d raised to the log base b of n power. Now don't despair how messy this looks. We can do some remarkable simplifications. So what I want to do next is I want to focus just on this 1 over b to the d raised to the log base b of n term. So that's going to be, we can write that as b to the minus d log base b of n, which if I factor this exponent into two successive parts, I can write this as b raised to the log base b of n power, and only then raised to the minus d. And now, of course, what happens is that taking the logarithm of n base b, followed by taking raising it to the b power, those are inverse operations that cancel, so that leaves us just with the n. So this results in a n to the minus d, and now, remarkably, this n to the minus d is just going to cancel out with this n to the d, leaving us with merely a raised to the log base b of n. And thus, out of this crazy sea of letters, rises a formula we can actually understand. So a to the log base b of n, if we step back and think for a minute, is actually a supernatural quantity. It describes something about the recursion trees that we already knew was supposed to pop up in the analysis. I'll let you think through exactly what that is in the following quiz. So the correct answer to this quiz is the fourth response. A raised to the log base b of n is precisely the number of leaves of the recursion tree. And remember, in our intuition for case 3, recursion trees where the amount of work is increasing per level, we thought that perhaps the work would be dominated by the work done at the leaves, which is just proportional to the number of leaves. So why is this the answer? We'll just remember what recursion trees look like. At level 0, we have a single node, and then with each level, we have 8 times as many nodes as before. That is, with each level of the recursion tree, the number of nodes goes up by a factor of a. How long does this process go on? Well, it goes on until we reach down to the leaves. Recall that the input size starts at n up at the root. It gets divided by a factor b each time, and it terminates once we get down to 1. So the leaves reside at precisely level log base b of n. So therefore, the number of leaves is just the branching factor, which is a, raised to the number of times that we actually multiply by a, which is just the number of levels, which is log base b of n. So each time we go down a level, we increase the number of nodes by a factor of a, and we go down a level log base b of n times, leaving us with a number of leaves equal to a raised to the log base b of n. So what we've done is we've mathematically confirmed in a very cool way our intuition about what case 3 should look like in the master method. We've proven that in case 3, when a is bigger than b to the d, the running time is O of the number of leaves in the recursion tree, just as the intuition predicted. But this leaves us with one final mystery. If you go back to the statement of the master method, we didn't say a to the log base b of n. In case 3, it says the running time is n to the log base b of a. And not only that, we've used this case 3 formula over and over again to evaluate Gauss's recursive algorithm for integer multiplication, to evaluate Strasson's matrix multiplication algorithm, and so on. So what's the story? How come we're not getting the same thing as in the statement of the master method? Well, there's a very simple explanation, which is simply that, believe it or not, a log base b of n and n to the log base b of a are exactly the same thing. This looks like the kind of mistake you'd make in freshman algebra, but actually if you think about it, these are simply the same quantity. If you don't believe me, just take the logarithm base b of both sides and you'll get the same thing on both sides. Now you might well be wondering why I didn't just state in the master method that the running time of case 3 is this very sensible and meaningful expression a raised to the log base b of n, i.e. the number of leaves in the recursion tree. Well, it turns out that while this expression on the left-hand side is the more meaningful conceptually, the right-hand side, n to the log base b of a, is the easiest one to apply. So recall when we worked through a bunch of examples of the master method, this right-hand side was super convenient when we evaluated the running times of algorithms, when we plugged in the numbers of a and b. In any case, whether or not you want to think about the running time in case 3 as proportional to the number of leaves in the tree or as proportional to n to the log base b of a, we're done. We've proved it. That's case 3. That was the last one. So we're done with the master method. QED. So that was a lot of hard work proving the master method, and I would never expect someone to be able to regurgitate all of the details of this proof. You know, it's something like a cocktail party. Well, maybe except at the nerdiest of all cocktail parties. But I do think there's a few high-level conceptual points of this proof that are worth remembering in the long term. So we started by just writing down a recursion tree for the recursive algorithm, and in a generic way, and going level by level, we counted up the work done by the algorithm. And this part of the proof had nothing to do with how A and B to the D related to each other. Then we recognized that there are three fundamentally different types of recursion trees. Those with the same amount of work per level, those where it increases with a level, and those where it decreases with a level. If you can remember that, you can even remember what the running times of the three cases should be. In the case where you do the same amount at every work at each level, we know there's a logarithmic number of levels. We know we do n to the d work at the root, so that gives us the running time in case 1 of n to the d log n. When the amount of work is decreasing with the levels, we now know that the root dominates. Up to a constant factor, we can throw out the rest of the levels, and we know n to the d work gets done at the root, so that's the overall running time. And in the third case, where it's increasing in the levels, the leaves dominate. The number of leaves is a raised to the log base of b of n, and that's the same as n to the log base b of a. And that's the proportion of the running time in case 3 of the master method.